In this presentation, we will consider how conducting land surveys using small UAVs, that is drones, compares with surveys using more traditional techniques such as airplanes and laser scanners. If there is one thing you should remember after watching this presentation, it should be that drones really are a disruptive technology in the field of surveying, offering an accuracy comparable to that of laser scanners, and with significant benefits in lower operating cost, ease, flexibility, and frequency of use, and the quality and type of data that can be gathered. In the rest of the presentation, we will try to convince you that this is indeed the case. Let's first look at the four major survey techniques available today. The first one is surveying using remote sensing satellites. Satellite imagery can provide a wealth of useful information, as we all know from Google Maps. However, remote sensing satellites suffer from poor spatial resolution, typically no more than half a meter, and a high temporal resolution, meaning that they can only revisit the same site once or twice a day. For these reasons, satellites are not feasible for topographical and building surveys. The second technique uses scanner-equipped ground vehicles and manned aerial platforms such as planes and helicopters. I call this low-definition surveying techniques, as the resolution of the generated point cloud is typically around 20 cm for ALTM, which is short for Airborne Laser Terrain Mapping, and around 5 cm for Vehicular Terrain Mapping, both of which are much lower than the density of point clouds obtained by laser scanners and the drones plus photogrammetry method. The third technique is laser scanning. Laser scanning has taken the world of surveying by storm in recent years by making it possible to obtain highly detailed and accurate point clouds of as-built structures in a reasonably short amount of time. However, while laser scanners offer unparalleled utility for indoor scanning, they can be time-consuming and unwieldy for outdoors usage. The last technique is a combination of collecting aerial imagery from drones and photogrammetry to create dense point clouds, textured 3D models, depth surface maps, and geotips from the aerial imagery. We will compare ALTM and laser scanners with a combination of drones and photogrammetry according to four metrics: cost, which includes both fixed and variable cost; type of data collected; the accuracy and quality; and the ease, flexibility, and risk of operations. The metrics for terrestrial laser scanning using ground vehicles falls between that of ALTM and laser scanning. Also, in our discussion of ALTM henceforth in this presentation, we will assume that the area platform is equipped with a 20,000 points per second camera. Let us consider first the fixed cost of ALTM, laser scanners, and drones. Entry-level ALTM platforms typically cost many hundreds of thousands of dollars to buy and around $10,000 in recurring expenses per year. Mid-level laser scanners from Leica and Faro cost around $100,000. In contrast, entry-level consumer drones cost around $1,000, and $5,000 can buy you some quite sophisticated drones capable of carrying heavier payloads with multiple sensors and longer flight times. The recurring cost for a drone is typically just a battery replacement per year, which runs around $50. The variable cost mainly consists of the pilot wage for all three platforms and the fuel cost for ALTM. The fuel cost depends upon the type of ALTM platforms. For two-seater planes and helicopters, about $50 is a good ballpark. The labor cost for ALTM is typically higher, as typically two operators are needed, one for flying the ALTM and another for operating the laser scanner. Let us now consider the question of how much does it cost to survey 1 acre using ALTM, laser scanners, and drones. As you can see, drones are a clear winner here due to their higher productivity than laser scanners and a far lower cost of operations. In this analysis, we assume that the surveyor is actually renting an airplane at $125 an hour. Most survey companies typically don't own their aircraft fleet, choosing instead to rent the aircraft as and when needed. Our numbers are backed up by this quote from a happy customer who used drones to survey the steep canyons in the Republic of Macedonia, a landlocked Balkan nation of mountains, lakes, and ancient town. We should also note that the data that can be obtained from drones is of significantly higher density and accuracy than that obtained from scanners mounted on planes. We will consider why this is so later in this presentation. Before we consider the types of data that drones allow us to gather and the quality and accuracy of that data, let's briefly digress to understand a key difference between laser scanning and photogrammetry. As implied by the word scanner, laser scanners calculate the distance of a point from the scanner in real time by shooting a laser beam and noting the time that it takes for the beam to reflect back. In this technique, distances are measured directly at the time of observation and measured one by one. The 3D position of a point in the scene can also be determined if the position of the scanner itself with respect to the world coordinate system is known accurately. However, the accuracy of the 3D position is subject to errors in determining the position of the scanner. For ground-based laser scanning, where the operator places a tripod-mounted scanner at a known fixed position on the ground, the position of the scanner can be determined very accurately. However, for airplane-mounted scanners, the position of the plane needs to be determined using RTK GNSS techniques, which are typically only accurate within a few centimeters. This constraint, along with the limitations on how accurately the orientation of the plane can be determined, imposes an upper bound on the accuracy of the resulting point clouds. Photogrammetry, on the other hand, operates using a fundamentally different principle. Photogrammetry relies on a series of overlapping pictures taken by a camera mounted on a UAV as the UAV flies over a terrain. The scene geometry is constructed from these pictures by a series of complex mathematical operations. Therefore, photogrammetry calculates both the camera positions and the scene geometry as a post-process step, unlike laser scanning where the distance of a 3D point is calculated directly and the 3D position of the point depends upon estimating the position of the scanner accurately. The 3D position of all points is estimated in the same step, unlike scanning where it is done sequentially. No prior information about the camera positions is needed, as both the camera positions and the scene geometry is calculated simultaneously during post-processing. And finally, the accuracy of the position estimate only depends upon the ground sampling distance, which in turn is a function of the megapixel value of the camera, the imaging sensor size, camera optics, and the distance of the camera from the ground. Let us now consider the rate at which scanners and cameras can gather data. Because cameras gather radiance information about the scene at once, they fundamentally can gather an order of magnitude more information than scanners that operate sequentially. Furthermore, scanners suffer from a trade-off between the data capture rate and the effective range. Higher the data capture rate, the lower the effective range. Let us now consider the accuracy of the data gathered by the drones plus photogrammetry method. As we saw earlier, scene geometry reconstruction using photogrammetry works by matching image features and thus fundamentally depends upon how well 3D scene points can be resolved in image pixels. A measure of how well 3D scene points can be resolved in pixels is the ground sampling distance, that is the GSD. GSD is defined as the distance between two consecutive pixel centers measured on the ground. The horizontal accuracy of photogrammetry is roughly 2 times GSD and the vertical accuracy is roughly 3 times GSD. The GSD depends upon the distance of the camera from the ground, the number of pixels, and the field of view of the camera. Let us now consider a simple example of a GSD calculation. As this calculation shows, a 12 megapixel Canon S100 shooting from 25 meters above the ground delivers pictures with a GSD of 0.8 centimeters per pixel, implying a horizontal accuracy of 1.6 centimeters and a vertical accuracy of 2.4 centimeters. So how does the accuracy of photogrammetry compare with that of terrestrial aerial laser scanners? As this table shows, photogrammetry delivers an accuracy that is much better than airborne scanners and only slightly worse than that of laser scanners. These calculations are borne out by data on the field, where accuracies of around an inch can readily be obtained with consumer-grade cameras. In fact, survey practitioners using drones for surveys for the first time are usually pleasantly surprised by the accuracy of the results generated. Moreover, these are the early days of the numerous applications of drones in surveying and architecture, and drone cameras are rapidly getting better. It's not too long before drones can deliver accuracies that rival the accuracies of laser scanners. A major development is the SiteScan package delivered by 3D Robotics, developed in collaboration with Autodesk and Sony. This package combines the versatile and easy-to-fly Solo drone from 3DR and the UMC-R10 camera from Sony that is custom designed for surveys with a recap photogrammetry software from Autodesk to provide an unbeatable package that will enable surveyors and construction companies to carry out aerial surveys of large sites and obtain detailed point clouds, depth surface maps, textured maps, etc. that can be readily imported into Autodesk 3D modeling and construction software. Let us now look at the quality of photogrammetry. the quality of photogrammetry is measured by the scatter or spray in the point clouds. Scatter is a measure of the variance of the computed 3D points from the true 3D surface. Scatter depends upon the sharpness and noise level of the photos, which in turn depends upon many factors such as the lighting conditions, the UAV flight speed, imaging sensor size, the quality of the lens optics, and so on. A high quality point cloud is important as it enables the modeler to easily visualize and mark the surface represented by the point cloud. Let us now look at a couple of examples. The first one is an example of a low quality point cloud. You can see that there is a large number of points both above and below the surface in question. The second one is a good quality point cloud. You can see that the points tightly adhere to the 3D surface. Let's now look at the other types of data that can be obtained from drone surveys. Unlike airborne and terrestrial laser scanners whose primary output is 3D point clouds, the drone plus photogrammetry technique delivers many different types of data such as textured meshes, geotiffs that can be easily overlaid on Google Maps, contour maps, and depth surface maps in the same post-processing step that generates the point clouds. The textured meshes can be used to create beautiful fly-arounds by animating a virtual camera and can also be used inside game engines to gamify your site. For example, visualize your site under different lighting conditions, bring other 3D objects into the site, and simple physics simulations. Drones can also be readily equipped with infrared cameras that can be used to create a heat map of a building, which can be great for obtaining a LEED certification, and hyperspectral cameras that find numerous applications in precision agriculture, carbon dioxide and methane emission detection, etc. And people are even trying to mount miniaturized LiDAR systems on drones, which can be particularly helpful while creating point clouds of forests and densely wooded areas where photogrammetry doesn't work as well. Another big benefit of drones is that they offer useful trade-offs between the accuracy and time required to conduct a survey and the accuracy and equipment cost. For example, in order to obtain more accurate and higher quality point clouds, one can fly the drone closer to the ground at the expense of taking longer to finish the survey. Alternatively, one can equip the drone with a higher resolution camera at the expense of a bigger and more expensive camera and a drone that is capable of carrying the heavier payload. Lastly, let's take a look at some operational considerations. Drones are a lot smaller, lighter, and easier to transport than laser scanners. A consumer drone can easily be transported in a small car and on a passenger plane. Drones are also a lot easier to use in hilly and geographically difficult areas such as ravines, valleys, canyons, etc., which can be inaccessible to planes or laser scanners. Laser scanners also need a line of sight to survey to areas being surveyed. This implies that a laser scanner needs to be transported to multiple locations on the site in order to obtain full coverage. A drone, being an airborne system, can simply fly over an obstacle, considerably lowering the time that it takes to finish a survey. Last but not the least, let's consider the risk of an accident. Risk is a product of the probability of an accident occurring and the severity of the damage caused by the accident. While software systems used on manned planes have to meet highly stringent safety standards and are extremely safe, flight control systems used on consumer drones are becoming safer as they are being used by millions of people around the world, and malfunctions such as brownouts and flyaways are becoming rarer. Moreover, the severity of the damage caused by a drone accident is a lot lower than a manned airplane accident. Therefore, in most scenarios, drones offer a safer and less risky alternative over manned planes. We have reached the end of the presentation. I hope that I've been able to convince you that drones outperform or are competitive with terrestrial and airborne scanners in cost, accuracy, the types of data collected, and the ease of operations. Thank you for attending.